Alright, today we're going to be going ahead and looking at how different data filling algorithms basically affect the PSP and how fast you can go ahead and get. So without further ado, let's go ahead and get right into it. The first two algorithms I have is pretty much the most naive version of a write that you could do. It goes from for int x equals 0, x is less than 16, y equals 0, z equals 0, and it goes x, y, z, and it basically just fills in the entire block. And this index, the first one is just kind of in a random order, whereas the one over here is in a more linear order. The reason why this is different is because it's going off of the y value, whereas this one's going off of the z. What this causes is that this has to do an unaligned write. So it's not like the data is right next to each other, it has to go jump somewhere else to go ahead and get it. Whereas over here, it's like right beside it. So if we go ahead and actually run this, we end up finding that, wow, surprise, the one that has aligned data is a lot faster. So here's a slightly different example. This is based on a much larger set of data. And so basically we're going to be using 128 for the y, so 16 by 16 by 128. So we slightly change up the way that it looks, but the only two differences is that y is xyz here, and this one is xzy, and y is the last value. So we can write directly sort of in a line series, and what this ends up doing is drastically showing the difference between the results. So if we go ahead and run it here, as you can see, it's taking almost, well, less than a quarter of the total time that it would normally take for it to generate. Alright, so now what I did for data fill number 3 here is, instead of taking this and then executing this per every case, we're instead doing a single fetch and a single calculation here, and then we're going to go ahead and only fill those within the calculation. This of course assumes that our chunk is zeroed by default, but in the case of this, it actually is, and it's guaranteed to be by default because of the way that it's initialized. So we can actually take advantage of this and then go ahead and only generate up to a specific amount. So we only have to go ahead and take up this much time to determine what should be here. So if we go ahead and run it, as you've seen from some of these results already, it's taking even faster, multiple magnitudes of order way faster in order to do that, because the average value of the map is not really that high. And even if it were, it would never be all the way filled up. Usually the map is only around, on average, about half filled. So if the map is only about half filled with data, the maximum this will go up to is about like 1700 microseconds, or 1.7 milliseconds. So this is already a very fast algorithm. So these are some interesting results. What I tried to do here was go ahead and, since we're using uint16t, extend it to the full uint32t, and instead just go ahead and double the value. But it appears that in the loop unrolling assembly, it's actually already doing this step for me in here. It's doing it way better than I am. So it actually ends up being a speed decrease. So I thought that was a really interesting thing to note. So I'm going to go ahead and see what other methods I can go ahead and try. So here's an important thing. The conditional statements that run inside of a data fill actually are very important. So you have to try to minimize the amount of data that you're trying to write here, because otherwise it's going to cause a lot of issues. So separately, you would have to do steps like adding ors and things like that would definitely have to be added as a separate step, because as you can see, it really does not like it. It really takes a lot of time to manage with what it's doing here. It takes about almost 50 or 60% performance hit to go ahead and do that. So you're going to have to minimize the number of things you want to do. So at max, maybe 3 or 4 to keep acceptable data filling times. All right, here we go. This is the final amount of time that it ends up taking to fill out the entire chunk. So it takes 64 total chunks generating and filled within 56.893 milliseconds, and that's pretty fast in general. When we add this to the total time it takes to generate the map, which is 128, it takes around 2.9 to 3 milliseconds or so to fill one individual chunk. So it's pretty good overall time. So that's from start to end, it takes 3 milliseconds to generate a chunk. That's pretty nice. The last part of this is cave generation and adding extra sort of pieces to that. So tomorrow I actually want to try one more experiment on doing this, and I think it would be really cool. Would be generating either filling the data into chunk or generating the chunk itself on the media engine, if I can go ahead and get that working. If so, that would really reduce the amount of total time taken, because you can start generating chunks simultaneously, and at that point you basically can get up to 2 times performance benefit overall, and that's pretty promising overall.